going to move into our last couple sections of chapter number 13 and be talking about fossil fuels, that being one of the sections, and power being the other section. Some of the things that we'll be talking about today is we're going to be talking about how these fossil fuels are formed, what energy conversions are used in the formation of fossil fuels, and then the last thing we're going to be doing and looking at that last section is we're going to be talking about power. Coal. When we talk about coal, a lot of times you think of coal being used for trains. Coal is another thing that can be used for heat and things like that. But where does coal come from? Okay, we know that we dig it up from the ground, but eventually when we talk about coal's going to be coming from a fossil fuel, something that died many years ago and took a long time to form because of pressure and temperatures. A fossil fuel is just going to be any material like coal that is going to be burned to release its chemical energy. Okay, and we'll be talking about getting that chemical energy from coal in our energy conversions. But as we said, fossil fuels come from the decay of dead animals over numerous years. Doesn't necessarily have to be an animal. It can be a plant, it can be a tree, things like that. But most of the time it is going to come from some dead animal from many years ago. An energy conversion, just remember, was going from one thing to another. If you woke up this morning and you had a piece of toast, okay, thinking about that piece of toast, electricity was needed to run that toaster. When you press the button down or press the handle down, all of a sudden heat was produced. Also, electromagnetic energy was produced in it because you can see that those coils turned red. So fossil fuels contain energy that originally came from the sun. And there's going to be a four-step process in us getting that energy from those fossil fuels. Now, as we said, it came from the sun. Remember, we've talked about in the sun, the fuel of the sun is hydrogen. When it fuses together, those two hydrogens become helium, also releasing another form of energy, electromagnetic energy. Electromagnetic energy, that's going to be our sunlight. So that sunlight comes down to the earth. Yes, it does warm it, but because we're talking about these fossil fuels, we need to talk about what's going to use the electromagnetic energy. And the electromagnetic energy is going to be used by the plants, chlorophyll, that process being photosynthesis, in the creation of C6H12O6, basically the creation of that food. And things like that that animals are going to eat. So in the creation of that food, we have chemical energy. Now, there's bonds in that food, in the grass, in the leaves, things like that. Okay, so that's going to be our chemical energy. Now, whether the plant dies, the flower dies, the animal eats that stuff, it dies, whatever. Okay, so right now we're at the chemical going on within the plant tree or the animal that has ate it for the energy coming from it. But now we're at the process of something dying, the plant, the animal, the tree, whatever. And many years pass by and all of a sudden we get the coal still having all of that chemical energy, but once we burn that coal, we get the thermal energy. So when I look here, okay, we've got our sun, and looking at that sun, we've got all of the nuclear energy going on within here in the process of fusion. Okay, all of a sudden the sunlight comes down, sunlight shines on those trees, and through that, and that's our electromagnetic energy. The energy from the sun, that electromagnetic energy, is taken in by the trees in that process of photosynthesis. C6H12O6 ends up being produced. That's our food, that's our glucose, our simplest sugar. And all of a sudden, they're saying here that tree dies in the swamp. Okay, many years later, temperature, pressure, that coal is formed. So nuclear, to sunlight being electromagnetic, to chemical, to the coal, which is chemical, but what we're going to say is we end up burning that coal to get the thermal energy. We burn fossil fuels to release that stored potential chemical energy for a variety of reasons. Okay, so here's our chemical energy, there's the coal, all of a sudden we heat it up. Okay, that's that thermal energy. All of a sudden it's turning that turbine, that generator here, as that's turning, that's mechanical energy. Mechanical energy is now converted into electrical energy. That electrical energy gets to your house, and in this case they're using a blow dryer. All I need you to do is know that coal gets us to thermal, and after that we really don't care where it goes. Okay, so that 4-step process from a couple of slides ago. So we use coal for heat. We take that heat, converts to electrical energy, etc. Like I said, the energy here being that blow dryer, which is also thermal energy. All right, so it says, what can you tell me about the amount of work done when? Okay, so I've got this person, they're going to carry 6 boxes from a basement upstairs in 20 minutes. And when we look at person B, they're going to carry 6 kind of identical boxes upstairs, but it's going to take them 4.5 hours. You know, they stop, they watch their favorite Netflix, stop to get a drink, go to the bathroom, whatever. Okay, so who did more work? So think of this. What is work? Work was force times a distance. So if we have 6 boxes, that's the same. And if we go from the basement to upstairs, the distance is the same. So therefore the work done is exactly the same. But when I look at this up here and we know that work's the same, what is different? And I'm hoping you look up here and say that the difference is going to come from the time. 20 minutes versus 4.5 hours. So what we need to do is we need to find a way to measure how fast that work gets done. And in looking at how fast that work gets done, that's going to be power. Power is just going to be the rate of doing work. So the equation for power is going to equal, power equals work divided by time. Okay, power equals work divided by time. If you want, you can say P equals W divided by T. So let's go ahead and let's look at the units. Okay, we learned that work was measured in joules. The SI base unit for time is seconds, and what we're going to do is we're going to have power measured in watts. So when we go ahead and we look at the circle equation, okay, our circle equation is going to end up looking like this. Okay, so there's our circle equation. What we're going to do is we're going to put the work up top, power and time are going to be on the bottom. So if we go ahead and we fill in our units, okay, we said that work was going to be measured in joules. We said time was going to be measured in seconds, and what that's going to do is that's going to leave us our power being measured in watts. Notice these two W's are different. This W, the one in blue, is going to be work. The one here in black is going to end up being watts. So if work isn't given, we do have an alternate equation, okay, because we do know how to find work, where we said work was the force times the distance. So power equals, we can say FD, this right here, F times D, that's going to give us this work up here, and then we're going to end up dividing it by time. So it says here we have a machine has a power rating of 1500 watts. How long does it take to do 3500 joules of work? So if we go ahead and we look at this equation and we look at our circle equation of work, power, and time. Okay, so that's supposed to be a P there. Okay, so when I look here, how long? So I'm trying to find this one right here, the time. So we're going to take the work, there it is, 3500 joules. So 3500 joules, we're going to divide it by the 1500 watts, and when you do that, okay, so that's going to be our time equals. So when I take 3500 and I divide it by 1500, you find out that you end up with 2.33 seconds for it to do that much work. Okay, if we look down at the bottom one, this one says how much power does a person have if they apply 350 newtons while pushing an object 10 meters, and it took the person 45 seconds. So when I look at this one, this is one that's going to be like what I just got done talking about. We don't have a joules number in there. Okay, we don't have a joules number. we don't have a work. So I'm going to end up having to take the force times the distance right up here in order to get that work value. Then I can divide it by the time. So if I go ahead and do this one, okay, 350 newtons, and we're going to multiply it by that distance that we moved it, 10 meters, and we end up dividing it by, it says here, the 45 seconds of time. Okay, that is a 5 here. Okay, so there's 45 seconds. So if you do that, if you take 350 times 10, okay, so I've got 3,500 joules. This portion right up top here, 350 times 10 meters, that's going to give me my amount of work, which is going to be 3,500 joules. When I divide that by the 45 seconds, you end up with 77.78 watts. Okay, so 77.78 watts worth of power. Let's go ahead and talk some units. Okay, a watt is going to be a very small thing. I mean, if we're talking about light bulbs, yeah, maybe you've seen a 60 watt bulb, maybe you've seen a 25 watt bulb, maybe you've seen a 100 watt bulb. But when we start talking about appliances like TVs, when we start talking about cars, when we start talking about machinery and tractors and things like that, a watt's going to be a very small unit. Even when we talk electricity, watt is going to be a very small unit. So oftentimes you see power being measured in kilowatts to express it. If you think of your stair steps, okay, we're about 3 steps away from kilo. That's the top of our step. To notice there's no prefix here, so that's going to be our base. So there are 1,000 watts in 1 kilowatt. Now an older unit for power is going to be the horsepower. A lot of times when they talk NASCAR, when they talk drag racing, when they just talk automobiles in general, they talk about how many horsepower that engine can put out. So a couple of other conversions that we have for power. 1 horsepower is 746 watts. If we're going to kilowatts, notice that 1,000 difference, okay, 3 zeros, so we've got it moved over here. 0.746 kilowatts is also going to be equal to 1 horsepower. Let's go ahead and look at a couple of conversions. I'm not going to do a watts to kilowatts one because that's one very similar to your stair steps that you've done. So when I go ahead and I look here, it says convert 2,384 watts to horsepower. So I'm going to go ahead and set up my railroad track, and because these are not based on thousands, tens, hundreds, and so forth, you have to do the railroad track here. So I'm going to go ahead and put up top here my 2,384 watts. Okay, remember how the railroad tracks worked, okay? In order for things that we don't want to cancel out, so the W is going to go down here, the horsepower is going to go up here, and if you think back to that previous slide, we had down 1 horsepower is going to be equal to 746 watts. So I go ahead and I fill it in. Okay, find the W, watts. There it is right there, 746. So I'm going to put that 746 right here. Okay, horsepower. Well, there's the number right there, just a 1. So the horsepower will always have the 1 with it. So when I take 2,384 and I divide it by 746, okay, remember top bottom we divide, you end up with the answer being 3.20 horsepower. And the reason why it's horsepower, because watts on the bottom, watts on the top, those cancel out, leaving us that only unit right there of horsepower. Okay, let's look at this one here. Okay, we're dealing with horsepower in kilowatts. So if I look at this one, okay, the conversion from the last slide was 0.746 kilowatts. Okay, so what I'm going to do is I'm going to draw my railroad track up here, and we're going to start off with the 342 horsepower. Okay, 342 horsepower. So to cancel things out, we know that the horsepower is going to go there. We know that the kilowatts is going to go there. Again, our top bottom to cancel out. So now, horsepower. There's the horsepower. Okay, so now the horsepower, the number 1 is going to go on the bottom because it has to match up with where horsepower is here, which horsepower is on the bottom. What we're going to do is we're going to end up putting our 0.746 with the kilowatts on top, because kilowatts, 0.746. Okay, notice horsepower going to cancel. Okay, horsepower is going to cancel. So when the numbers are both on top, what we end up doing is we end up multiplying. When you punch into your calculator 342 times 0.746, what you end up with is 255 .13 kilowatts. So that's how we convert between horsepower and watts and horsepower and kilowatts.